As I said, we'll start this section by doing a few example problems related to thermal expansion. Let me read the first one and then we'll reduce this and do the work. A steel beam, coefficient of linear expansion 12 times 10 to the minus 6 per degree centigrade, 12 meters long, sits next to a concrete wall when the temperature is 20 degrees centigrade. A gap must be left between the beam and the concrete wall for the expansion purposes. If the temperature rises to 45 degrees, how large must the gap be if the steel beam just touches the concrete wall? Now, for the purposes of this problem, we're going to disregard the potential expansion of the wall itself. Although you could have a linear expansion for the wall and a length of the wall as well. But for the purposes of this problem, we're not going to do that. So let's take a look at how we would go about doing this. First of all, we know that delta L is equal to L alpha delta T. And so it's equal to L, which is 12 meters, alpha, which is 1 or 12, well, let's say 1.2 times 10 to the minus 7, and delta T is 25 degrees. That's delta T. So if we put delta L in there, it's going to be 12 times 1.2 times 10 to the minus 7 times 25. And so the change here is going to be 3.6 times 10 to the minus 3 meters, or 0.36 centimeters. And so you have to leave a gap of approximately, let's say, 0.4 centimeters to ensure that the metal does not hit the wall. Now, if the wall has the same length and the same change here, then you'd have to double the gap because the wall would move toward the beam and the beam would move toward the wall. Let's look at the second problem. You have a 500 cubic meter mass of air, and it gives you the volumetric expansion, and it's in a shop of 20 degrees. How much does the volume of this air change if the temperature is lowered to 0 degrees? Well, delta V is equal to V beta delta T. And in this case, it's going to decrease, okay? So we're going to go with 500 cubic meters times 3,400 times 10 to the minus 6 times, and the change in temperature is minus 20 degrees. If you do the math here, you get 3.4 times 10 to the minus 1 cubic meters, and it shrinks by that amount. The third problem says a metal rod 0.5 meters is heated from 15 degrees centigrade to 95 degrees centigrade. The length of the rod increases by 0.96 millimeters. What is the coefficient of linear expansion for the rod? Well, if we write our formula down, delta L is equal to L alpha delta T. We solve for alpha here. So alpha is equal to delta L divided by L delta T. So alpha is equal to, delta L is 0.96 millimeters, which is 9.6 times 10 to the minus 4 meters, divided by, and it's a 0.5 meter rod, and the change in temperature is 80 degrees. So alpha is going to be, if you do the math here, 2.4 times 10 to the minus 5 per degree centigrade. Let's move on to talk about ideal gases. When you put air inside a balloon, and what they do in these is generally heat this air up. And because it's hotter than the ambient air, it results in an in a buoyant force, which pushes the air or pushes the balloon up. There's one of two ways that you can do a balloon. The most common is what we call a hot air balloon. A hot air balloon is a balloon that's filled with air, the same as the ambient air in terms of its composition, but it's heated such that it causes a rise. It rises up and causes a buoyant force. The other way is to put a substance, a gas in there that is lighter than air, such as helium or hydrogen. And this is how something like the Goodyear blimp or the dirigible, the Hindenburg, were operated. Now with gases, for something to be called an ideal gas, you have to make certain assumptions. And the most common assumption is to say that the molecules are so widely separated from each other that they do not exert any force or any resistance on each other. Other things is you neglect the volume of the actual molecule, and the collisions that occur are assumed to be absolutely elastic. And given those assumptions, the pressure times the volume is equal to the number of molecules times a constant times the temperature, where the constant, when you're dealing with the number of molecules, is 1.38 times 10 to the minus 23 joules per degree Kelvin. Now, it's very difficult to measure individual molecules. And so what we do, as you know, having been in chemistry class, is we look at a mole of molecules. A mole of molecules is 6.02 times 10 to the 23rd molecules. And if these were the size of table tennis balls, they would cover the Earth to a depth of 40 kilometers, or about 2.5 times the height of Mount Everest. So if we change our formula and change n from the number of molecules to the number of moles of molecules, then the formula looks like something we've seen before, which is pressure times volume is equal to the number of moles times the constant R times T. The constant R is based on the units of the other factors, particularly the units of pressure and volume. If the pressure is expressed in pascals, or newtons per meter squared, and the volume is expressed in cubic meters, then the R is equal to 8.31 joules per mole degree Kelvin. Now let's work some problems with this ideal gas law. When filling a weather balloon with gas, you have to consider that the gas will expand greatly as it rises and the pressure decreases. Let's say you put about 10 moles of helium into a balloon that can inflate to a size of 5,000 liters. Now 1,000 liters is equivalent to a cubic meter. And so 5,000 liters is approximately 5 cubic meters. Currently the balloon is not full because of the high pressure on the ground. Atmosphere on the ground is 1.01 times 10 to the 5th pascals. What is the pressure when the balloon rises to a point where the temperature is minus 10 degrees and the balloon is now completely filled with gas? So let's take a look at how we would do this. We know that PV is equal to nRT. And we want to know the pressure, so we solve this equation for P. And if we put the numbers that we know, 10 moles, and we'll use the 8.31 for the gas constant, and the temperature is minus 10 degrees, so that's 273 minus 10, so 263 degrees Kelvin. And that's going to be divided by the volume, which is 5,000 liters, but 5 cubic meters. So the pressure, if you do the math here, comes out to be 4,000 or 4.371 times 10 to the 3 newtons per meter squared, which is the same as pascals. Now that's 100 times less than atmospheric pressure. And so that's a very low pressure, although it looks like a pretty big number. Let's look at the second problem. Calculate the pressure in a 212 liter tank that has 23.3 kilograms of argon gas at 25 degrees. Again, we're doing pressure, so let's just write that same formula down that we had up there. And if we need the moles, I looked it up, the molecular weight of argon is 40 grams per mole. So I changed the kilograms to grams, divide that by 40, so that's the number of moles. We'll use our same 8.31, and the temperature here is 25 degrees centigrade, or 298 if you add 273 to that, Kelvin. And the volume here is 212 liters. If you divide that by 1,000 liters per cubic meter, it's 0.212 cubic meters. And so the pressure, if you do the math here, is 6.8 times 10 to the 6th newtons per square meter, or pascals. And you've got a huge number of moles in a very small volume, and so that should tell you that you're going to have a pretty high pressure. The last one says what volume is occupied by 5 grams of oxygen at 28 degrees and a pressure of 998 atmospheres. Now remember, 1 atmosphere is approximately 1.01 times 10 to the 5th pascals. So we want volume this time, and if we solve this equation for volume, we get the same sort of equation, except it's divided by pressure instead of volume. And so that's going to be 5.03 grams. The molecular weight of oxygen is 32 grams per mole, times 8.31 again, times, and the temperature here is 28, plus 273 is 301 degrees Kelvin, divided by 0.998 times 1.01 times 10 to the 5th pascals per atmosphere. If you do this calculation, you get 0.039 meters cubed, and if you multiply that by 1,000, it's 3.9 liters of gas. Let's finish up this lecture by talking about phase changes. And you've seen these pressure volume diagrams before in chemistry, but I'm going to go over them again because I think they're an important concept. A pressure volume diagram assumes a particular temperature, and the graph is a graph that measures pressure versus volume of a substance. Now here's an example of several pressure volume diagrams at different temperature points. If you look at the A group of curves, which are on the left, each curve is what's called an isotherm, which means that it's at a particular temperature and shows the relationship between pressure and volume at that particular temperature. The higher curves are fairly nice hyperbolas because they are at a higher temperature. The lower curves are not hyperbolas because the substance is not a gas throughout its entire pressure, and it goes through a period where it is a liquid equilibrium. And in those situations, the line becomes flat, you'll notice. On the right is lower temperatures, or an expanded portion at the lower end of temperatures. And what you can see is that when it passes through this vapor region, it becomes flat again. And the curve on the right is called a saturation curve. Now this is a typical pressure volume diagram that you probably remember from chemistry, but I'm going to go over it again with you. First of all, if you look in the upper right, you see something called the critical point. In this case, it's a very high pressure, 218 atmospheres, which is 218 times the atmospheric pressure. And you see that this is at a temperature of 374. That's called the critical point. This is a temperature and pressure where a liquid cannot exist. In other words, there's no liquid here, vapor only. The critical pressure is the minimum pressure needed for a liquid to exist at the critical point. So as you go down, you see that 218 represents the least pressure. Above that point, there is only vapor. Okay, so above the critical point, there's only vapor. So this pressure, 218, is the minimum pressure where a liquid can exist. The triple point, which is to the left and down, is a point of pressure and temperature where the substance in the diagram exists in all three phases. That is, it exists in the solid phase, the liquid phase, and the vapor phase. Now, at any pressure and temperature, you should be able to tell whether the substance is going to be a solid, a liquid, or a gas. Now, here's another way of looking at it. A shows the rates of boiling and condensation that are equal at a particular temperature. And what you can see is that you reach an equilibrium where the vaporization of the liquid and the condensation of the gas are at the same rate. Now, if you raise the temperature in the container, you get the situation in B. In this situation, you have a higher temperature, the boiling rate or vaporization rate is higher, but the condensation rate also becomes higher. Now, this occurs because the pressure in the container goes up. As a result, you reach another equilibrium, but that equilibrium is at a higher temperature and a higher pressure. A is a situation of saturation, where 100% humidity has been reached. B is what's known as a way of measuring relative humidity. That is the amount of water that's in the air relative to the maximum that can occur at any point. The dew point is the temperature where the relative humidity is the same as the saturation. Now you have 3 beakers, and you see that the temperature is going up in each beaker. In the first beaker, a small air bubble occurs. In that air bubble is water vapor at 20 degrees, the amount of water vapor in 20 degrees, and it's saturated with the amount of water vapor that you see at 20 degrees. As the temperature goes up, that bubble gets bigger because the vapor pressure increases, and the bubble continues to expand to keep its pressure the same as 1 atmosphere, because that's the pressure that's being exerted on the top of the surface of the liquid. However, when you reach 100, the water vapor gets high enough that it becomes 100 as well, or 1 atmosphere, and it rises to the surface and explodes and then releases its water vapor. And that's what's known as boiling. So with evaporation and boiling, there are certain substances that never go through a liquid phase, and those substances go through phases in normal situations of directly from a solid to a vapor. And that direct passage from a solid to a vapor is known as sublimation.